Welcome to our channel. Today's topic is paging, a memory management technique used by operating systems. It divides physical memory and virtual memory into fixed size blocks, and the blocks in RAM called frames and in virtual address space are called pages. The operating system maps page to frames, which allows it to use more memory than what physically available in RAM, and also reduce the external fragmentation. Before we divide in, a couple of things to keep in mind. The smallest addressable unit in RAM is 1 byte. Pages and frames are the same size, but they are not the same thing. Pages are virtual, frames are physical. Now here we have a simple hand-drawn diagram describing a system, and below it a sample problem we will work through. The system specs are frame size or page size is 18 kilobyte, the index 1 is 8 bits, the virtual address is 32 bits, and the flags are 6 bits. This system uses a two-level page table structure. That number can go up or down depending on the system's need. More levels means you can manage larger address space, but the address translation gets slower since you walk through each level one by one. Fewer levels means simpler, faster system, but you are limited to smaller address spaces. Now, a virtual memory address has three parts: index 1, index 2, and an offset. Index 1 tells us which entry to pick inside the level 1 page table. That entry holds a frame number which points to one of our level 2 page tables. Then index 2 tells us which entry to pick inside that level 2 table. That entry's frame number points to the actual physical frame in RAM. And the offset tells us exactly which byte within that frame we are after. So index 1 and 2 tells us which frame to go to, and the offset tells us where inside that frame the data lives. Alright, let's go into the questions. Question 1. How many bits are used for the offset index 1 and 2? The smallest addressable unit is 1 byte, so our formula is 2 to the power of offset length times 1 byte is the frame size. The offset must be able to point to every byte within a frame. So if the frame size is 16 kilobyte, we need to 2 to the offset times 1 byte is 18 kilobytes. Let's count up. 2 to the power 10 is 1 kilobyte, and 2 to the power 11 is 2 kilobyte. 12 is 4 kilobyte, 13 is 8 kilobyte, so 14 is 16 kilobyte. So the offset is 14 bits. Index 1 is already given to us 8 bits. 14 bits for the offset, 8 for index 1, that's 22 bits total. We have a 32-bit virtual address, so the remaining 10 bits go to index 2. That's our answer. Offset 14 bits, index 1 8 bits, and index 2 10 bits. Question 2. How much memory can a single level 2 page table address? Each entry points to one frame, and each frame is 16 kilobyte. The number of entries is 2 to the power of 10, so 1024. 1024 times 16 kilobyte is equal to 16 megabyte. One level 2 page table can address up to 16 megabyte. Question 3. How many level 1 page table does each process have? This is an important conceptual point actually. Each process has exactly one level 1 page table, also called the root page table. Index 1 picks an entry inside of the level 1 table, and that entry points to a level 2 page table. But we never talk about an index that selects which level 1 page table to use, because there's no such a filter, such an index like that. There's always exactly one level 1 page table per process. It's fixed. That's what makes it the root. Question 4. How much RAM can a 32-bit virtual address space address? Using our formula, 2 power of the 32 unique addresses times 1 byte each is equal to 4 gigabyte. That's the one of the classical limitations of the 32-bit systems. With 64-bit addressing, you get into the terabytes, so it's a huge difference. Last question. What are the size of the level 1 and level 2 page tables? Level 1 always has exactly 2 power of index 1 entries, used or not. It's fixed. Level 2 page tables are created on demand, only where needed, but we will calculate the maximum for both. Each entry stores a frame number plus flags. Frame number bits, index 1 and index 2, 8 bits and 10 bits, 18 bits. And at 6 flag bits, 24 bits total. We round up the nearest clean size, 32 bits equal to 4 bytes per entry. Level 1 page table, 2 power of the 8 entries times 4 bytes, 256 times 4 is 1 kilobyte, and level 2 page table, 2 power of 10 entries times 4 bytes, 1024 times 4 equal to 4 kilobyte. Those are the maximum size of for each level in this system. Now let's move on to our second topic, page faults. A page fault happens when a process tries to access a page that isn't currently in RAM. The two most common causes are, first, the data has never been loaded into RAM at all. Second, the operating system swapped it out to disk because it hadn't been used in a while. In this problem, we will focus on the first scenario, data being loaded for the first time. We have a media player, same system, frame size is 16 kilobyte. Video file is 48 kilobyte and audio is 16 kilobyte and subtitles are 8 kilobyte. Two questions. One, how many page faults happens, and the second one, how much level 2 page table space do we need? For the page faults, video 48 kilobyte divided by 16 kilobyte, 3 frames, 3 page faults. Audio 16 kilobyte divided by 16 kilobyte means 1 frame, 1 page fault, and the subtitles 8 kilobyte within 1 frame, so 1 page fault. Total 5 page faults. For the level 2 page table size, we have 5 frames, so we need 5 entries. Each entry is 4 byte, and as we calculated before, 5 times 4 bytes, 20 bytes, that's the level 2 page table space needed for this scenario. And that's a wrap in this video. Hope it was helpful. If anything was unclear or if you spotted a mistake, feel free to leave a comment below and take care of yourself. See you next time.